Okay, we'll get started. I hope you were able to review the material so far. So instead of continuing with the rest of the module, I thought we will do a small tutorial session before we move on to the rest of the module. Okay, this will essentially be tutorial problems on whatever we've learned so far: vector spaces, subspaces, linear independence, span of vectors, norm, and inner product. Okay. These are essentially problems from the notes. So if you've gone through the notes, these are probably already familiar to you. Maybe we'll just discuss them in case the examples were not very clear to you by just reading through the notes. So we looked at what is a vector space, right? We defined what a vector space is. What is a vector space? Yeah, you'll have to be louder. And if you're not sure, use that sheet. That's the purpose of the sheet. Okay, it's closed what? Yeah, okay. Okay, all right. Yeah, so vector space is a set that is closed under vector scaling and vector addition. Okay. All right, so we've seen that elements of Rn or sets like this, Rn or Cn, are vector spaces, right? And we had defined vector scaling and vector addition operation for this. And we found that for the defined vector scaling and vector addition operation, the Cn and Rn are actually closed. So they do form a vector space. Well, the elements of Rn, they're essentially a linear arrangement of numbers, okay, of n numbers. Okay. We will now look at another arrangement, which is an extension of this. If you can have a line, I can also define a rectangular arrangement of numbers, basically what are called matrices. We will look at matrices more deeply in the next module, but let's just define what a matrix is. Matrix is simply a rectangular arrangement of numbers. Okay. In vectors that we've seen so far, we have a number associated with the vector, which is basically the size of the vector, which is the number of elements in the column that you have. With matrices, you will have two numbers. You'll have the number of rows and number of columns. Let's call n comma m, or let's call it p comma q. Okay. First one is the number of rows. Next one is the number of columns. Okay. Now, if you have an arrangement of numbers like this, let's say all of them are real numbers, then you would say this is a set P cross Q. Okay, that's a representation of set of all matrices with real numbers with P rows and Q columns. Okay. See, in effect, it's no different from essentially what you have are PQ numbers, right? It's just you've chosen to arrange them in a particular fashion. You could have very well had written those numbers as RPQ vector. That means just a linear arrangement of numbers. Okay. And we know RPQ is a vector space because any Rn is vector space. So RPQ, PQ is just another integer number. So it is a vector space. Right. Now, what we want to know is if this RP cross Q, this is a vector space. Okay. Now, to verify whether or not this is a vector space, we need to first define two operations, right? What is the corresponding scaling and addition operation? Okay. For Rn, we know what the definitions are. We've defined how to do vector scaling and vector addition. We'll do a similar definition for matrices as well. Okay. Okay. Let's say A is a matrix with elements A11, A12. These are subscripts used to identify each element at a particular row and column. Okay. Well, here I've written M cross N. So there are M rows and N columns. Okay. For a matrix like this, we define matrix scaling as C multiplied by the matrix. And notice that whenever we deal with matrices in this course, they will always be represented by capital letters and that are bold. Okay? This is bold capital A, so that represents the matrix. Scalar multiplication is exactly the same as vector addition. You simply multiply each element of the matrix by C, the scalar. In Rn, what were the conditions for adding two vectors? When can you add two vectors? Yes, they have to be from the same space, right? Similarly, here you can add two matrices only if they have the same number of rows and same number of columns. That means they're from, in this case, both of them have to be from Rm cross n. Okay. And the addition operation is similar to what we did in n vector addition. You simply add the elements corresponding to the same index. You do the same thing here. You add the elements corresponding to the same row and column number. Okay. So the first element of A plus B will be A11 plus B11. Second element in the first row will be A12 plus B12 and so on and so forth. Right? And these two are our definition for, so we have the set R M cross N set. We've defined the vectors scalar multiplication and vector addition operations. Now I ask you, for this set with the defined scalar multiplication and vector addition, is R M cross N a vector space? How would you verify this? What do you think? Is this a vector space? If yes, you have to explain why. If no, you have to tell me why not. What is the first thing you test? You should ask what is the zero element here. Let's define the zero element. Zero element is simply matrix of all zeros. That's a zero element. Is it there in R M cross N? Zero is a real number. This is a matrix of all zeros. That means matrix of all real numbers. So it has to be in R M cross N. Okay. So zero is there. So we have to do more work. What is the first thing you test? Vector scaling. So, okay, if A is an element from Rm cross N, you do the vector scaling by some C. Each of these elements is also a real number because C is a real number. Aij is a real number. Each of these numbers is a real number. That means this matrix is a M cross N matrix of real numbers. That means it must be there in Rm M cross N. That means this set under this definition of scalar multiplication is closed. Right? If I take any element from there multiplied by scalar, I'll find that resulting matrix in the original matrix or original set. Sorry. Similarly, if A and B are matrices from Rm cross N, A and B elements of A and B are real numbers. According to the definition of vector addition, each of these elements of A plus B will also be in Rm cross N because any Aij plus Bij is also a real number. Right? That means the resulting matrix is a matrix of M cross N real numbers. That means it must be there in Rm cross N. That means it's also closed under vector addition. That means this set here is closed under vector scaling and vector addition. That means this is a space. So not only are n vectors vector spaces, M cross N matrices are also form vector spaces. So by the definition, a matrix can also be called a vector because it's an element of a vector space. Okay, but we will call it a vector nevertheless. Oh, sorry, matrix nevertheless. Okay, is it clear? Sure. Okay. So so it turns out matrices are also vector spaces, and in fact, it's easy to show that C M cross N will also be vector space. Yeah, I leave it as an exercise for you to think about. Now we go to another very different type of entity. Okay. So far, we've seen simply an arrangement of numbers, a bunch of numbers arranged either in a column or in the form of a matrix, and we found that they in fact form vector spaces. Now we look at something slightly different. We look at the set of all polynomials of a specific order. Okay. If I say I have an nth order polynomial, I am essentially saying I have a polynomial which is a function of x, some unknown variable. Okay. The expression for the polynomial would look like this. Right? For example, if I say second order polynomial, quadratic polynomial, then that would look like this. B a naught plus a1x plus a2 square. If I have a cubic polynomial, then it's simple. I have cube. But if I have a nth order polynomial, then I would simply have actually here there is a mistake. Here I've written is less than or equal to. So this should be n, not n minus 1. Okay. And these AIs are real numbers. And for now, let's assume x only takes values between some values between a and b. Okay. That means you can visualize this polynomial like this. This is the value of x. You can plot p of x, and this is the value of this is a, and this is b. If we had a bunch of zeroth order polynomials, they would simply be horizontal lines, right? Because you only have a naught. So a naught can be any real number. That means your functions would be essentially lines like this, each one corresponding to a different polynomial, because each one corresponds to a different value of a naught. If I had a first order polynomial, then they would essentially look like this. All lines, straight lines, or line segments between a and b. If you had second order polynomial, then all sorts of parabolas between a and b and all that, right? So those are the different possible polynomials that you have, okay, for any given order. Okay. Now, let's say we have a set P. I'll call it Pn. This is a set of all polynomials of order less than or equal to n. That means this includes polynomials of the form a0 plus a1x, a0 plus a1x plus a2x square, so on and so forth to a0 plus a1x an x power n. Okay. The most general form is this. If you make any of the ai 0, right, then that term simply disappears. For example, this would be the example where a1 to an are 0. This would be an example where a2 to an are 0. Okay, so the general form is like this. Okay, so if I have a set that has polynomials of this form, and we define a scaling and addition operation. Okay, the scaling operation is defined like this. You take p of x, which is an element from the set, and when you say you're scaling it by a scalar c, all you're doing is you're multiplying this expression on the right hand side by c, and the regular rule of real number algebra applies, right? That means the resulting polynomial will be of this form. You multiply each of the coefficients ak by c. Okay. Now, the set that we started with were polynomials with whose coefficients were real numbers. Okay. What results here? The coefficient of the resulting polynomial, when you do the scaling operation as the way we've defined it, is also a real number. That means if p of x is from the set set Pn, then c times p of x must also be in the set Pn, right? That means the set of polynomials of order less than or equal to n with real number coefficients are closed under scaling operation as defined here, right? We similarly know how to add two polynomials, right? If I take two polynomials, p of x and q of x, right? from Pn and add them together. You know how to add them. You simply add the coefficients corresponding to x with the same power, right? So these are the two polynomials, Px and Qx. If you add them together, the resulting polynomial will be of this form, where you simply add the coefficients ak and bk corresponding to the power xk, corresponding to the power k to x. Okay? And ak and bk are real numbers. Ak plus bk will be a real number. That means the resulting polynomial is a polynomial of order less than or equal to n, okay, whose coefficients are real numbers. Right? That means this polynomial should be in Pn as well, because Pn is a set of all polynomials with order less than or equal to n, whose coefficients are real numbers. Means in the way vector addition is defined here, this set of polynomials is also closed under this addition operation. So it's closed under scalar multiplication, it's closed under vector addition. That means the set of polynomials should essentially form a vector space. So in fact, it is a set of polynomials of order less than or equal to n forms a. So now we find, the point of showing this is that the idea of what is a vector space is more general than just a bunch of numbers. So Rn, we started with, well, real numbers were was a vector space. A set of real numbers was a vector space. When we took more than one real number, Rn, that turned out to be a vector space. And we had a rectangular arrangement of numbers, again, still a bunch of real numbers, that turned out to be a vector space. Now we are finding the set of polynomials are also of a given order are also vector spaces. You look at one more example. In fact, not just polynomials. Let's say you have a bunch of functions, f of x. Essentially, I've written these are continuous functions, okay, where x takes on values between 0, 1. That's what the symbol stands for. C 0, 1 means these are all continuous functions for the values of x between 0 and 1. Okay. So, for example, if you were to draw these, right? This is x, this is 0 and 1. Any fancy function you can draw, as long as it's continuous, right, is in the set 0, 1. C 0, 1. Okay. And we've seen before, if you have a function f of x, we can do a scaling operation where you simply take the function. When you say you're scaling it by a factor c, you're simply taking the function, computing the value of f of x, whatever value comes out, you simply multiply that number by the scalar. That's the scaling operation. Okay. So for example, if I had a function like this is my f of x, and let's say I'm multiplying it by a factor 2 times f of x would simply be this. Well, it'll not exactly like that. Probably like this, depending on the exact value of f of x here. That's scaling. We similarly know how to do vector addition, right? So if you had two functions, f of x and g of x, we simply compute the value of f of x and g of x for a given value of x. What you will get two real numbers, and you simply add them. That is essentially now the new function f of x plus g of x. Okay. And one thing, of course, I did not say is the values that f of x produces are also real numbers. Okay. That was probably obvious, but I'm just making it explicit. Now, if you have a continuous function between 0 and 1, if you multiply it by a scalar, the function will remain continuous. That means c times f of x is a continuous function between 0 and 1. That means it must be in c of 0, 1, because c of 0, 1 contains all possible continuous functions from 0 to 1. Similarly, if you add two continuous functions, the resulting function will also be continuous. That means the resulting function must be there in the original set C of 0, 1. So C of 0, 1 is also a set of functions with a finite domain and which are continuous also turn out to be vector spaces. Okay? Right. So I hope this at least makes it clear to you that this idea of vector spaces is actually more general than just a bunch of numbers. Okay? And all of that rests on this idea of a scaling operation and a addition operation. And we know that geometrically, the two of them essentially produce flat spaces. Okay, so in a way, it goes on to say that a set of polynomials, set of continuous functions, all form flat spaces. If you take subspaces in these original big spaces, they will all be flat geometrically. There is no curvature to them. Okay, so that's essentially some examples of how you would verify if a given set of given set is a vector space or not. Okay. Now we'll extend that idea and then look at subspaces of some original vector space. Okay, you have to do the same process, essentially verify if it's a vector space or not. Okay. Earlier in the class we discussed that if I represent this as R2, and we said lines passing through the origin are subspaces of R2 because they are subsets of R2 and they also are vector spaces by themselves. That means they must be subspaces. We primarily use a geometric approach to show this. Okay. Now we will do the algebraic version of that. Okay. Now I know that elements from R2 look like this. Right. If I take an element from R2, it will be like this: x1, x2, where x1 and x2 are real numbers. Okay. This is x1. Okay. But if I take elements from this red line, right, what will those elements look like? I'm going to call this S. If I take elements from S, they will still have two numbers, right? See, here, when I take any element from x1 and x2, any element from R2, x1 and x2 are completely independent of each other. Right? I can choose any value for x1 that has no bearing on what value I can choose for x2. Right? For example, I can choose a point here, here, here. It doesn't matter. That is equivalent to saying I can choose x1 and x2 freely. But if I want to choose elements from S, right? Can I choose x1 and x2 freely? No, I can't. That's correct. So let's say this is a line with slope m. The line has a slope m. If it has slope m, tell me if I take one point out of this line, right? Say this point or this point, any of these points, what will be the two elements x1 and x2 in this case? They cannot be completely independent of each other. If I choose x1, x2 is already determined for me. If I choose x2, x1 is determined for me. Because I'm constrained to be in that line. I cannot freely roam around in this entire two-dimensional space. Yeah. So what would it be? So if I choose x1, what would be the corresponding x2 value? So essentially, if I choose this value, this value is fixed for me. If I choose x1 freely, the corresponding value of x2 here is fixed for me. What will it be if the line has slope m? Be m times x1. Okay, you can verify why that is later on. Okay, so whenever I take elements from this red line, right, they will always be of this form. Okay, or if you say I want to freely choose x2, then x1 is determined for me. x1 will be x2 by m. I cannot freely choose. For example, if to make that slightly even more clear. Let's say we're talking about this line. What will be if I choose an element from this line, right? What will those elements look like? What is the slope of that line? 0. I can choose any value for x1. What will be my y value or the x2 value? Well, see, it's this line, no? That line corresponds to all x2 values where x2 is 0. So this is always 0. Okay? Similarly, if my line was this, then the elements from this line will look like 0, x2. I can only choose x2. x1 is fixed for me. This is when the slope m is 0. Here, this is when the slope m is actually infinity. And here, the red lines are lines with finite non-zero value for the slope. Okay? And if you take any element from S, it'll look like this. Now the question is, can you show that the set of elements of this form, which are essentially elements from this red line, are a subspace of R2? What would you have to do? What are the conditions? Subset, and it should be a vector space. It's a subset of R2, so that's done. What about the verification of whether it's a vector space? What is one of the first things you test if it's a subspace? 0. Does it have the 0 element? Yes or no? Yeah, it does. It does, right? For example, if I choose x1, 0 element is both of them have to be 0. If I freely choose the first element, x1 to 0, the second element is automatically 0 because the second element is of the form m times x1, m times 0. So 0, 0 is there, right? So that's done, okay? So it can be a vector space by itself. So how do we verify the other two? Scaling, okay. If you take any element, we have x1, m times x1. If you scale it by some factor c, you will have c times x1, m times c times x1. Okay, now the question is, you have a new vector resulting from the scaling operation. Is this vector in S? Yes? Okay. If yes, why? You'll have to explain why you think it's in S. You'll have to be louder. You're speaking to yourself, so you'll have to tell me a little louder. I won't hear otherwise. Hey, okay. What we are trying to do here, forget about the geometry. I'm trying to essentially show you how to do this algebraically. Geometrically, we saw it's a subspace. So this vector here has to be in S, right? Because we already know it's a vector space. But I'm trying to essentially show what the argument would be algebraically to show that it is actually closed. Okay, the argument is simple, right? Elements of S essentially look like this one or this one. If the first element is x1, the second element is m times x1. Okay, so any vector of the form where the first element is some value and the second element is m times that value should be in S. Okay, that's the definition of the straight line. We started with this. This is a element in S. We scaled it by C by the definition of scaling in R2. What we get is this. Okay? Now here the first element is C times x1 and the second element is m times C times x1. That means this is an element. This must be in S because elements of S look like if first element is x, second element is m times x. Here the first element is C times x1. The second element is m times C times x1. That means this has to be in S. Right? That means it's closed under vector scaling. This red line, elements from this set. Right? What about vector addition? Can you use a similar line of argument and then explain to me why it's closed under vector addition? To do vector addition, you have to take two elements, not just one. Okay? Let's say we take x1 m times x1 and the other element we take is y1 m times y1. If I add these two, what do I get? I will get x1 plus y1. I'll get m1 x1 plus mx1 plus my1, right? And I can write this as x1 plus y1. And the second element would be m times x1 plus y1. Does this element belong to S? But it does, because what do elements of M look like? If the first element is some value, second element is M times that value. The first element is x1 plus y1. The second element is M times x1 plus y1. So this is also closed under vector addition. That means the set S actually forms a vector space by itself, right? It's a subset of R2 and it's a vector space. That means it has to be a subspace of R2. Okay. Right. This one, I want you to do it and tell me. These are sets of this form. I'm calling this set S. Okay. If I take any element from this set, what will that look like? Okay. If you're not sure, what is the general equation for a line in a plane in R2? Sorry. Yes. What is this mx plus c? If you call this y and if you call this x, you know the equation for the line is. That means if you have the x value, the y value is determined by this expression on the right hand side, which is m into x plus c. Okay. We don't use x and y when we are dealing with, at least in this course, we call this x1, this x2, which essentially says x2 equals m times x1 plus c. I'm simply using different variables for the horizontal and the vertical axis. Right? That means if I choose elements from this set S, right, they should be of this form, right? The first element is x, which is some value for x1. The second element has to be mx plus c. Now tell me whether or not it's closed under or whether it's a vector space. And for now, assume, no, you don't have to assume anything. The only thing is m and c are real numbers. That's all. Is S a vector space? No, why? Sorry? Yes. What is the constancy? Why is it a problem? Sorry? No. Here, the set that you have here is a multiple of x1 plus some c. You're saying the presence of c is a problem. I'm asking why. Here, whenever you have to verify, please go back to those three things you have to test. Is 0 in that set? Is vector scaling okay? Is vector addition okay? Is our vector addition and vector scaling close? Just verify that. How would you verify that? Is 0 there in the set? Is the 0 element there in the set? Why not? Well, if you substitute 0 for x, the second element is c. If c is non-zero, then the 0 element is not there, then you know it's not a vector space, right? So the 0 element is present only if c is 0. Okay, that's one. Okay, let's still do the scaling and let's still verify the scaling and the addition properties. See if they are closed. Is this closed under vector scaling? You'll have to show it algebraically. The only thing you have to verify is if you take an element from here, we take an element from this set. First element is x, second element has to be mx plus c. Whatever the value of the first element is, the second element has to be mx plus c. So if you take an element from that set and you scale it, is the resultant vector, does it have this form? What will it have? What will it look like if you do scaling? Let's say we scale by alpha. You take x mx plus c, and you scale by some scalar alpha, what do you get? Huh? Yeah, alpha x m times alpha x plus alpha c. Now the question is, does this have this form? Well, if this were to have this form, it should look like this. If the first element is alpha x, the second element has to be m times alpha x plus c. If this point, right, will be in the set S. But look at this. It's m into alpha times x, that's okay. But what the second element is alpha times c, which means it's not there except if c is 0. Okay, right. So not closed under vector scaling. Okay, what about vector addition? You can verify and tell me. Where does it fail? You can tell me where it fails. So the way you would start is you take two elements from the set S. Let's call it x1 and call it x mx plus c. This is one element. Take another element y my plus c. If you add them together, what do you get? X plus y and mx plus c plus my plus c. So we can write it as m into. Now the question is this part of the original set that you started with? Why not? Yeah, yeah, you're right. What is it? Yes. If this were to be part of the original set S, if the first element is x plus y, the second element should be m into x plus y plus c. But what you have is plus 2c. That means this is not there. Means this is not closed under vector addition also. And this is what we saw geometrically, right? For example, if you take a point like this, right, and you scale it, it will go out of the line. If you scale it by a number greater than 1. If you take two vectors like this and you add them together, the resulting vector will go out of the line. So this point, when you scale, is out of that line, and this point, when you add 2 points, goes out of the line. That's why it does not look like elements from your original set case. Okay. All right. Now we know that lines not passing through the origin actually don't form a subspace of R2. You do this and tell me. Parabola passing through the origin. Is this, the question is this a subspace of R2? It looks like this. You take any point from this parabola of the set S, it will look like this. If the first element is x, the second element is half times x square. Okay. So what all would you test? And tell me 0 is there? Is 0 there according to the algebraic definition? Yes, if you substitute 0 for x, the first element, the second element is also 0, so 0, 0 is there. Okay, all right. What about vector scaling? What do you get when you scale? What do you get? So if you take x half times x square, what do you get when you scale it by some c? Cx and half Cx square. Is this in the original set? Yes. Why do you say it's there in the original set? What? See, if you were to be there in the original set S, what is the condition you need to satisfy? The condition you need to satisfy is if the first element is x, the second element has to be half times x square. What is the first element here? Here, sorry, in the scaled version. Cx. So what should be the second element? Half of Cx, is it not Cx, no? Okay. For you to be in this set, if the first element is Cx, the second element has to be half Cx square. That means it should have been half C square x square. But what you have here is half Cx square. That means this is not closed under vector scaling. Okay, all right. What about vector addition? Will be x plus y. This will be half of. The question is this closed under vector addition? Yes or no? See, if a vector has to be part of S, if the first element is x plus y, what should be the second element? It should be half of y whole square. What is the half of x plus y whole square? What is this? This is only x square plus y square. There is no 2 times xy. That means this is not closed under vector addition also. So this is not a subspace. It's a subset of R2, but not a subspace because it does not satisfy the properties of a vector space. Okay, all right. So that's all I wanted to say about, or I wanted to discuss about vector spaces and subspaces. We'll now move on to looking at linear independence. Okay. What is linear independence? We'll first look at problem 1.9, but let's look at the definition first. What is linear independence? It's a property of a set of vectors. Okay. When do you say a set of vectors is linearly independent? Yeah. Yeah. No, no. It's not the definition, no. Sorry. Sorry. Okay. Yeah. So if you have a set of vectors v1 to vn, and you take their linear combination, and we want the linear combination to produce a zero vector. If the only way you can produce a zero vector is when your alpha, all the alphas is zero, then you say that set is linearly independent. If there is any non-zero value for your alpha 1 to alpha n that can produce the zero vector through a linear combination, then that set is linearly dependent. Okay, that's all. That's the definition. So using that definition, the question is now if you had a set of vectors like this, where v1 is this vector and v2 is this vector, is this set linearly independent or dependent? Okay. If you have to verify, you have to simply blindly apply the definition. The definition is this. So if to test whether the set of these two vectors forms a linearly independent set, I take the two vectors 1, 0, multiply first one by alpha 1. I essentially take their linear combination and equate it to, okay. If I expand out the left hand side, I'll get alpha 1 plus 0, 0 plus alpha 2, which is equal to alpha 1, alpha 2, and I want this to be equal to 0. The only way the left hand side will be equal to the right hand side is if alpha 1 is 0 and alpha 2 is 0. That means the only values of alpha 1 and alpha 2 that will produce the 0 vector through a linear combination operation is if alpha 1 and alpha 2 are 0. That means this original set that we started with, the set of 1, 0 and 0, 1 vectors has to be a linearly independent set. Okay, that means there is no redundancy in the set. Okay, all right. Now we have three vectors instead. We have v1, v2, just like the ones in the previous problem, and we add a third set to this. v3 means we have now 1, 0, 0, 1, and some strange vector 23 minus 5. Now the question is this set a linearly independent set? How would you verify? Well, you apply the same procedure and tell me. The linear combination of this has to produce the 0 vector. Well, you do the linear combination. You take alpha times the first vector, take alpha 2 times the second vector, alpha 3 times the third vector, and then the left hand side will simply be alpha 1 plus 23 alpha 3, alpha 2 minus 5 alpha 3. This is equal to, if I substitute alpha 1, alpha 2, alpha 3 equals 0, then the left hand side is equal to right hand side. But that's not enough. 0 alphas will always produce the 0 vector. But the question is the 0 alphas is the only combination that will produce a 0 vector? Is there any other value for alpha 1, alpha 2, and alpha 3 that you can choose from the left hand side that will still produce the 0 vector, apart from alpha 1, alpha 2, alpha 3 equals 0? Yes, if I choose alpha 3 to be 1, alpha 1 to be minus 1 by minus 23, and if I choose alpha 2 to be plus 5, then I'll get the 0 vector. That means there is at least one non-zero combination. Alpha 1 equals minus 23, alpha 2 equals plus 5, alpha 3 equals 1, which will produce a 0 vector. That means this set is not linearly independent, it's dependent. Okay, using that argument, now tell me whether this vector, it's a set with only one vector from R3. Is this a linearly independent set? Here, just blindly apply the rule. Linear combination equals 0. And then figure out, from that, see if you can figure out if you can make an argument about the alpha i's that will produce a 0 vector. Yes, why? So, okay, what is the linear combination of this one vector? Alpha times minus 1, 1. If you take the alpha inside, then it's minus alpha, alpha, alpha. This has to be equal to 0. The only value for alpha that will produce a 0 vector is 0. So this is in fact linearly independent. Okay, all right. What about this? A set containing only the 0 vector from R3. Is that a linearly independent set? Yes or no? Linearly independent? Why is it linearly independent? Again, you don't have to think too much. You simply blindly have to apply the rule. What is the rule? How do you verify? Linear combination produces 0. Yeah, so take the linear combination and tell me whether alpha equals 0 is the only way you can produce a 0 vector. No, you started with the 0 vector. So here, I need to produce this. Because I started with the 0 vector, alpha could be anything. Could be any non-zero value and I would have still produced a 0 vector. So in fact, this is not a linearly independent set. Okay, all right. So that's all I wanted to do. I don't think I have anything else for the tutorial. Okay. Please go back and review this if what we've done is not entirely clear to you now. But as I keep repeating, it's initially you still have to just have to blindly apply the rule to verify and get comfortable with it. Okay. I'm going to stop here unless there are any questions so far. No? We'll continue with the lecture. Oh, that's one. Okay. Now, let's say we start with the set Rn. Okay. And I randomly choose a vector from Rn. Okay. Some vector v1. Okay. And then I form a set. And then I can ask you, is this set linearly independent? Okay. You can't say yes or no unless and until you know what is v1 exactly. This set of just one vector from Rn will be linearly independent as long as v1 is not the 0 vector. If it's not the 0 vector, then it's linearly independent. Okay. Let's say I have a linearly independent set. That means v1 is not 0. I take another vector. Okay. From now on, we'll assume we're not going to take the 0 vector. None of the vectors I will take from now on will be 0, because if any one of them is the 0 vector, then the resulting set is linearly dependent. Whenever the 0 element is there, it's linearly dependent. I take v2, non-zero vector, and I ask, is this linearly independent? Again, you can't say, it depends on the values of v1 and v2. As long as v1 and v2 are not collinear, this will be linearly independent. Okay. I can continue this process. I'll take another one, and I could ask linearly independent. Here you would say if they are not coplanar, then if all three of them don't fall on the same plane, then they're linearly independent. And I can keep continuing this process. And you can keep getting a linearly independent set only until a certain point. Beyond that point, if you keep adding to that vector, or to that set, sorry, if you keep adding to that set, the set that we are building, it'll turn out that set becomes linearly dependent after a particular point. See, because we're talking about, when you say linear independence, we're talking about, is there redundancy in the set? There is only so much stuff I can add before things become redundant. That means the new thing that I'm adding, that information was already present in the previous guys who were in that set. Right? So there is a limit to how big a set you can form from a vector space Rn before that set for sure is linearly dependent. Okay? It turns out that limit is essentially this number n. Okay? From Rn, you can only choose a maximum of n vectors, all non-zero vectors, and still have the possibility of having a linearly independent set. If you take more than n vectors from Rn and form a set, that set for sure will be linearly dependent. Okay? That means if you have the real line where n is 1, you can choose one non-zero number and form a set, let's say 1, and that set will be, well, can be linearly independent. Okay. The moment you add one more element to the set, let's say I add 1 and 2, it becomes linearly dependent. And then any more elements you add, it's linearly dependent after that. Similarly, if you're talking about R2, I can choose two elements that are not collinear and form a linearly independent set. The moment I add a third element, the set will be linearly dependent. Similarly, in R3, you can at the most choose 3 and form a linearly independent set. The moment you add a fourth element, you become linearly dependent. Okay. So that's what is written here. A linearly independent collection of n vectors from Rn, can at most have n vectors, not more. The moment you add more than n vectors, that set becomes linearly dependent. Okay. And that's essentially what we've discussed here. Whether you talk about the real line or R2 or R3, stuff like that. Okay. And we also discussed earlier this. Okay. If you have a set of vectors, and if you represent a new vector y as a linear combination of the elements from that set, the linear combination, essentially the values of alpha, that determine the value y, is unique when the original set that you started with was linearly independent or dependent. Okay? If you had a linearly dependent set, there are infinite number of ways in which I can produce an element from the span of that set. If it's linearly independent, then there is only one way in which I can produce an element from the span of that set. Okay? And both those ideas, this and this, bring us to this idea of the basis for a vector space. So basis, say basis for a space. That means you can also have a basis for a subspace, because subspaces are also vector spaces. Okay? A basis is essentially a set of vectors, okay, that satisfy two properties. It's linearly independent. Well, I've actually written it here. It's linearly independent, and well, I've written the definition slightly different here, but they're all connected. It's linearly independent, and it spans the vector space from which you choose it. Okay, that's the general definition. Linearly independent, and it can produce any element in the original vector space through a linear combination operation. That's what it means to say spans the entire vector space. If you're talking about a basis for Rn, then again you say the set needs to be linearly independent, and the set has a size n. That means there are n vectors in it. So in Rn, if you have a set of n vectors, n different vectors that form a linearly independent set, you will say that's a basis for Rn, because you can take the linear combination of elements of that set and produce any element in your original vector space Rn. Okay? So your basis essentially now allows you to generate any element in your original vector space. And because it's linearly independent, it allows you to produce each element in your original vector space in a unique manner. That means there is only one way you can produce a particular vector from your Rn. Okay, let's look at an example. Okay, before so that it becomes a little less abstract. Okay, we're talking about R2. Okay? A basis for R2, we can at the max have two vectors, because the moment I take the third one, the set will become linearly dependent. That means the first condition is not satisfied. If I have less than two, right, from R2, if I have only one, it turns out it cannot span all of R2. It will only span a line in R2. Right? I need two to span all of R2. Right? So I take two vectors. Right? For now, I'll take, let's say, this vector, this vector. Okay, and these are essentially the E1 and E2 vector. E1 is 1, 0, 0, 1, 0. E2 is 0, 1. Okay. Now, if I want to produce any vector x1, x2, okay, the question, I can use E1 and E2. So E1 and E2 are linearly independent. We saw earlier in the tutorial, right? If I want to produce x1, x2 through a linear combination, that means alpha 1 times 1, 0 plus alpha 2 times 0, 1, which will be equal to alpha 1, alpha 2. For this to be equal to x1, x2, alpha 1 has to be equal to x1, alpha 2 has to be equal to x2. There is no other value for an alpha 1 and alpha 2 that will produce x1, x2. That means any vector that we have can be generated through a unique linear combination of my basis vectors. That's what I've written here. So whenever you have a basis, it's a linearly independent set. It spans all of our n or all of your vector space, which implies that any vector that you can generate from this using this, any vector in your original vector space can be produced through a unique linear combination of your original vectors that you started with. Okay. And let's say these are vectors from your vector space Rn. Let's say this is the basis for Rn. Now, if I take another element from Rn, because this set of x1 to xn is a basis for Rn, that means I can generate y as a linear combination of x1 to xn. That means I can generate it like this. So one way to think of this vector y now for me is, if you and I agree that we are going to be dealing with this basis, I'm going to call it x. This basis x, right? Then one way I can convey information about this vector y to you is by simply telling you what the alphas are. Because if I tell you the alphas, you can reconstruct y. Because both of us agreed we are going to work with x1 to xn vectors, use these vectors, right? That means these numbers alpha 1, alpha 2, alpha n, no, are in fact a representation of y in the, notice that alpha 1 to alpha n are a representation of y only if you choose to use the x1 to xn basis. If somebody else uses a different basis, z1 to zn, the alphas will be different. So for them, the representation of the number would be different. For example, maybe I have 11 keys here. Okay. If you and I agree to use the decimal system, the representation of the number of keys I have is 1, 1. But if you and I decide to use the binary system, the representation would be different. It would be what? 1, 0, 1, 1. If I use hexadecimal, it will be B. Right? The representation is different, but the count that all of us are talking about is the same. So which essentially brings us to this idea that the vector y is the point in space. But how I represent that point, right, will depend on what basis we are using. If you and I agree to use the x basis, then the numbers to represent y would be alpha 1 to alpha n. If we had a different basis, z1 to zn, then maybe y has a very different representation. Here, y would be represented by beta 1 to beta n, and these two, of course, will not be the same. Y, the reality is the same that we're talking about. It's just our representations are different. Difference between 1 1 or 1 0 1 1. Okay? Decimal versus binary. That's the idea. So that's what I've written down here. So these numbers alpha 1 to alpha n can be thought of as expansion of y in the x basis, or the representation of y in the x basis. So you in fact have infinite number of bases. So before we proceed, right, we'll just clarify this a little bit further. Let's say we have one basis like this. I'm going to call it v1, v2, and this is the point y. Okay. To get y through a linear combination of v1 and v2, I can use the parallelogram law of vectors. I need to scale y1 and y2 and then add them together. That means apply the parallelogram law of vectors so that I reach y, right? So the way I could do that is I scale y2 by so much amount, x2 by so much, sorry, y2 by this amount, y1 by this amount, and if I add them together, I'll get y. Okay? So this is alpha 2 times v2. This is alpha 1 times v1. And if I add alpha 1 times v1 plus alpha 2 times v2, I will get y. Okay? So here, alpha 1 and alpha 2 are the representation of this vector y in the v1, v2 basis. Okay? Now, let's say I use a different basis now. I'm going to draw a new figure. Same y, but instead of v1, v2, let's say I use a different basis. I'm going to call this W1. They are not collinear, so they're linearly independent. So W and W2 is the basis. Okay. Now, the way I would produce y is, let me draw a line like this. I drop a line from this point y to W1, which is parallel to W2. Okay. Okay. And similarly, I drop a line from this point y to W2 parallel to W1. Okay. Now, if I scale my W2 by so much, and if I scale my W1 by so much, and if this is alpha beta 2 W2, this is beta 1 W1. If I add beta 1 W1 and beta 2 W2, I will get this vector. I will get y. Okay. See, the point is the same. Y in space. I was using V1 and V2 to represent y. I would have to give you the numbers alpha 1 and alpha 2. If I was using W1 and W2 to represent, I would have to give you the numbers. Okay. So the point y has different representations depending on what basis you use. Okay, all right. So And it turns out there are infinite number of bases. I've only shown you examples of 2, but there are infinite number of linearly independent sets that you can choose from R2 of size 2. Okay. Turns out some of them are special. Okay. And these special bases are called orthonormal. Are called orthonormal bases. It's very simple. Okay. An orthonormal basis is a basis, let's say we are talking about Rn. An orthonormal basis for Rn is a basis for Rn where the individual elements of that basis set all have Euclidean distance 1. That means their second norm is 1 and they're all mutually orthogonal. They're all orthogonal to each other. That's essentially what is written here. If you have an orthonormal set of vectors for Rn, orthonormal basis for Rn, and let's say those basis vectors are x1, x2 to xn, then they satisfy this property. If you take the standard inner product of xi with xj, if I and j are not equal, that means two different vectors, then their inner product is 0. That means they are perpendicular to each other. If it's the same vector, if I equals j, that means what you get is the so x. Remember, x transpose x is simply the 2 norm squared. And we said these are all of length Euclidean distance or length 1 according to the Euclidean norm. That means the inner product of xi with itself will be simply 1. If you have a basis that satisfies this property, then you say it's an orthonormal basis. Okay? So here, I don't know if you've noticed, this is an orthonormal basis, the way I've drawn it here, V1, V2. Whereas this is not. Well, I've not drawn it properly, but here it's not orthonormal. W1, W2, not an orthonormal basis. Okay? The reason these are special is because of simplicity in the computation of the representation of a vector in a basis. Okay, for example, if I had a vector like this, these were two basis vectors, let's say V1 and V2. The way I would, what I would have to do geometrically, I would take this point, drop a line from the tip of this point to this V2 line that is parallel to V1, which will be like this. And then similarly here. And this is how much I need to scale V1. This is how much I need to scale, how much I need to scale V2. This is how much I need to scale V1 and add them together to get this point. The corresponding algebraic operation here is complicated, right? Because you need to find the equation for this line and then draw a line that is parallel to V1 but offset by a certain amount. So the algebra turns out to be complicated. But if you have an orthonormal basis, turns out the way you would calculate your alpha i's is very simple. Okay? For example, let's say we have an orthonormal basis x1 to xn for Rn. Because it's a basis, I can write y as a linear combination of my xi's, like alpha 1 x1 plus alpha 2 x2 and so on and so forth. If I take the inner product of the left hand side and the right hand side with respect to one of the basis vectors xi, okay, so the right hand side will look like this. But because it's an orthonormal basis, here, whenever I is not equal to j, the inner product will be 0. When it's equal to j, the inner product is 1. That means on the right hand side here, all terms will disappear except for one term, right? Except for the ith term. Okay? The inner product of xi with x1 will be, let's say I is not equal to 1. Inner product of x1 with xi will be 0, so on and so forth, except for xi transpose xi. That means xi inner product with y will simply be equal to alpha I. That means it's very easy for me to find the representation of any vector if I have an orthonormal basis. All I have to do is I take the vector to find alpha I alpha I simply take the standard inner product of my original vector y with that basis vector, and then I get alpha I. You don't have this simplicity if it's not orthonormal. That's one of the reasons why these are special. Okay. And in fact, if you had a basis like this for R2, is this an orthonormal basis for R2? Well, you just have to verify this. The length of each of these vectors is 1. You can verify that. Standard inner product between these two will turn out to be 0. That means they're orthogonal to each other and they have length 1, linearly independent set. Spans R2, that means it's an orthonormal basis. This is the corresponding geometry associated with how you'd find alpha i's for your, if you had an orthonormal basis. This is again something you're familiar with when you work, when you've done maths with the Cartesian coordinates. If you have a vector like this, you can find the components of the x component, y component, z component by simply dropping perpendiculars. The dropping perpendicular and then finding how much is the projection here, that's essentially this operation. Now, we saw that if you have a vector space, there are infinite number of bases for that vector space. Okay? But it turns out all of them will have one common property. Well, a few common properties, all of them are bases. That's something that's common between them. In addition to that, there is another property that is common among them, which is essentially the number of elements they have. Okay? It turns out that if you have R2, there are an infinite number of basis sets I can list. Turns out for R2, all these basis sets will only have 2 elements. All of them will be linearly independent. They will all span Rn. In addition to that, we'll find that all of them will have 2 elements. Okay? Similarly, if I take R3 and list all the basis sets, all of them will have 3 elements. And so if I take Rn, right, and list all the basis sets, they will all have n elements. So that number of elements that you have in a basis set is actually an important property. It turns out that is nothing but the dimension of the vector space that you have. Okay, that means the dimension of R2 is 2 because the basis set for that vector space contains 2 elements. That means, which essentially means you only need 2 vectors which form a linearly independent set to produce any element in R2 through a linear combination operation. Okay? Or equivalent to saying it has 2 degrees of freedom. I can move left, right, up, down. If I'm talking about R3, then left, right, up, down, front, back. R4, you have 4 degrees of freedom and so on and so forth. So the number n, or number of degrees of freedom for a vector space can be obtained from the number of elements in a basis for that vector space. Okay, that's called the dimension of a vector space. This is something very important. For example, now if you talk about subspaces are vector spaces. You can have a basis for a vector space for a vector space. That means you can have a basis for a subspace. You can talk about a dimension of a subspace, which is essentially the number of elements in a basis for that subspace. So that would mean if I have R2, the subspaces of R2 essentially look like this. What is the dimension of each of these subspaces? Well, it depends on how many elements the basis for the subspace have. Each of these lines that passes through the origin, the basis for any of those lines will only have one element. That means these are one-dimensional subspaces of R2. Okay. Similarly, if I have R3, lines that pass through the origin will their basis sets will have one element. That means they are one-dimensional subspaces. Planes that pass through the origin in R3 will, all the basis sets for those planes will have 2 elements. So they are 2-dimensional subspaces of R3 and so on and so forth. right? So in general, if you have a vector space Rn and a subspace S whose basis has m elements, that means that the dimension of that subspace S, we will usually write it as dim S, will be m. And notice m will be less than or equal to n. N is the original space that you started with. Okay. Okay. Now we come to the last topic for this module, is on linear functions. Okay. So very definition is again quite simple. A function f, okay, which takes elements from Rn. So it takes elements from a vector space and produces a real number. Okay, that's the definition of a function. Takes elements from Rn, produces a real number. So one way to think about this is Rn. This is the real line. This is f. It takes an element from Rn and produces an element in R. Okay. So we have a function like this. Okay, that maps elements from Rn to a real number. We say that this function is a linear function if it satisfies what is called the superposition principle. Okay, essentially it means if I have a vector x which under the map f produces some number f of x. Note x is an element from Rn, f of x is actually a real number. Okay, and I have another vector which under the map where f maps y to f of y. If this function is real, if the function, sorry, not real, if the function f is linear, okay, then if I take a linear combination of my vectors x and y, like I've written here, sorry, if I take the linear, I'm not applying f yet. If I take a linear combination of this will produce another vector which will be in Rn because Rn is a vector space. It's closed under linear combination. The resulting element will simply be, the resulting element should be of this form. If the function is linear, then this will be equal to alpha times f of x plus beta times. So this essentially means if the function is linear, that means the addition operation that happens inside the parenthesis can essentially come out. You can apply f individually to each of the components of this addition operation. Okay? And if it's linear, this scalar that you have inside can also come out. That's essentially what that means. If I know the output for the vector x, if I know the output for vector y, then I know the output of this function for all linear combinations of x and y. Okay? And this should be satisfied for all alpha and all beta and for all x and y. Then you say that the function is linear. Okay? That's essentially what is written here. Let's maybe do a couple of examples and then maybe that will become clear. If I have a function that gives me, let's say, I have a function like this. It takes in a vector from R2 and then returns essentially the sum of all elements of R2 or elements from that vector from R2. Okay. That means here f takes elements from R2 and produces R. Now, is f a linear function? Let's verify. If it's a linear function, right, it needs to satisfy the superposition principle. That means if I have x1, x2, the output would be x1 plus x2. If I have a vector y1 plus y1, y2, the output would be y1 plus y2. That's the definition of the function. If I now compute f of alpha times x1, x2 plus beta times y1, y2, then this will be equal to, well, I can simplify this. So this will be f of alpha x1 plus beta y1 plus alpha x2 plus beta y2. But if you input a vector like this, we know what the output will be. The output will simply be the sum of these elements, right? So this should be equal to alpha x1 plus alpha y1 plus beta. Oh, sorry. So alpha x1 plus beta y1 plus alpha x2 plus beta y2. This is nothing but, if I can take the alphas out separately, this is alpha times x1 plus x2 plus beta times y1 plus y2. But what is x1 plus x2? It's f of x1, x2. Similarly, y1 plus y2 is f of y1 plus y2. That means this is equal to that means this function is in fact linear, because f of alpha times x1, x2 plus beta times y1, y2 is in fact alpha times f of x1, x2, beta times f of y1, y2. Okay? So that's how you verify. And another very interesting fact is this. I mean, you can think of an infinite number of linear functions, right? From the definition, right? Functions that map Rn to R and that satisfy the superposition principle. And there are many functions you can think of, infinitely many. But the interesting bit is, if you're talking about linear functions that map from Rn to R, and whatever linear function you come up with, okay, that satisfies the superposition principle, it turns out all of those functions can be presented in this form. So any linear function that maps from Rn to N, Rn to R, f of x, can be represented as the inner product of your vector x, okay, with some constant vector w. Okay, and this vector w is again from Rn, because x is from Rn. Okay, so it turns out no matter what linear function you come up with, okay, we can always find a set of wi's, w1 to wn, such that the linear function can be written as w1 times x1, w2 times x2, so on and so forth, which is essentially saying we can represent the output of the linear function as a standard inner product between some vector w from Rn and your vector x. And in your assignment, you'll learn how to find. If I give you a linear function, let's say I give you a computer program, and I say this computer program represents a linear function. Whenever you input a vector from Rn, it will give you a real number. And this computer program then is a linear function. It turns out no matter what computer program I give you, that will produce that essentially is a linear function. You can always find the vector w to replace that the computer function I've given you, and you simply use that w to do the exact same operation that my program was doing. That's what it means to say every linear function can be represented as w transpose x by appropriately choosing w. Yeah? Okay. Right. So that brings us to the end of module 1. We will, so I'd say please go through everything that we've covered so far. If there are any questions that you have about module 1, we will discuss them tomorrow and maybe do another small tutorial for the rest of the things that we've covered. And then we will move on with the matrices module. After we finish matrices, then we will look at applications of vector spaces and matrices. We will look at some case studies. Thank you.